Hello again. Let me be the first to say congratulations on making it to this point in our Opti 202 training. Over the past day and a half, you've explored intermediate optimization techniques, you've tackled hands-on exercises with Jerry and Isan, and you've learned how to handle real-world complexities in your problem solving. And now, it's time to put it all together with our culminating case study. Today's example is a truly special one. We're thrilled to feature the incredible work of our social partner, ESUPS, Emergency Supply Prepositioning Strategy, and their innovative platform, Stockholm. Stockholm is a tool designed by ESUPS that leverages data science and optimization to improve stock visibility and coordination efforts among global humanitarian organizations in an effort to reduce response times once disasters strike. ESUPS is one of Gurobi's premier social partners under the Gurobi Gives Back initiative, and that initiative provides free, unrestricted licenses to qualifying nonprofit organizations working to achieve at least one of the United Nations Sustainable Development Goals. Now I'm going to hand it over to ESUPS to play a video of their work and a little bit more about the Stockholm platform.
Pre-positioning relief items is a preparedness mechanism embraced by most international and national humanitarian agencies. It allows to provide immediate assistance to affected people in an area, even if damaged accesses prevent help coming from outside. The problem is there is no strategy to coordinate decisions across agencies about what to preposition, where, and in which quantities. This leads to gaps, duplications, and cost and time inefficiencies in the prepositioning of critical items. So much so that the very purposes of prepositioning are severely impaired. With ESUPS, we want to tackle this problem by moving beyond coordination into active collaboration. ESUPS develops tools that allow all national and local stockholders to come together and define a collective prepositioning strategy. This framework allows each agency to then define its own plan, considering what others have, to reach optimum efficiency. When national authorities and responders know what the overall stock capacities in country are, they are in a better position to get what they lack. This is how ESUPS supports logistics localization, through a rebalancing of the push-pull approach, giving local decision-makers a stronger voice in what comes in their country. And this is how ESUPS works. Stock data is collected and displayed in the Stock of Humanitarian Organizations Logistics Mapping Platform, or Stockholm. Registered users can update data online autonomously, as often as needed, and filter data based on several parameters. Stockholm is free and connected to other platforms used in the sector. ESUPS runs two types of data analyses. First, an analysis on the last 40 years of disasters in each country to understand their impact on locations and affected people. And second, an analysis comparing the existing stock to the needed stock, should those past disasters happen again today. These analyses allow ESUPS to provide collective recommendations to all agencies pre-positioning in countries. These suggestions can help to move towards a more efficient way to pre-position relief items, saving both time and money. ESUPS also promotes a global change of mindset towards more collaborative preparedness activities. We work closely with academia to research underexplored practices, such as the possibility to pool resources through loan and borrowing stock, allowing for a smoother exchange of relief items. Visit our website for more information. And please share this video to help us promote ESUP's collective approach to pre-positioning.
ESUPS is a global collaborative working group that brings together NGOs, academics, UN agencies, and regional organizations focused on logistics preparedness. The team at ESUPS is focused on humanitarian stock prepositioning, and it ensures that disaster relief supplies are strategically placed to minimize response times and to maximize impact when disasters strike. And as you just heard in their video, one of ESUP's crowning achievements is its platform, Stockholm. Stockholm is a data-driven tool designed to improve coordination among humanitarian organizations. It's the first of its kind, and it visually maps global relief stock locations and uses optimization techniques to determine the best prepositioning strategies, enabling faster and more efficient disaster response times. So now a little bit about the importance of prepositioning. To understand why ESUPS work is so critical, let's briefly reflect on the 2015 earthquake in Kathmandu, Nepal. This is a devastating disaster that killed nearly 9,000 people, and it destroyed critical infrastructure, including the country's central relief supply depots. Despite an incredible global response, much of the aid arrived too late to save lives during those vital first 24 hours. This is a tragedy that highlighted the need for better logistics planning and coordination, which is exactly what ESUPS was designed to address. By optimizing the location and allocation of relief supplies, ESUPS is helping to ensure that aid reaches those in need faster and more efficiently than ever before, and they're achieving this level of efficiency at a global scale. So now for the case study. In this case, you'll step into ESUP's world and explore how optimization can revolutionize disaster response logistics. You'll delve into the challenges of humanitarian logistics, such as unpredictable disaster locations and coordinating across multiple organizations. Second, the optimization model, deriving Stockholm, which determines the best locations for prepositioning supplies. And last, hands-on exercises in a Jupyter notebook, where you'll work with real-world data to build, refine, and implement your own optimization model. A special thanks to the team at ESUPS, specifically Florent, Andrew, and Ben, Gurobi experts Ronald, Jerry, and our intern Ben Rapkin, and the ESUPS academic partner Jason for bringing us the case that you're going to be using today. So a little bit about why this case matters. This isn't just an academic exercise. The techniques that you're going to be learning about today reflect real-world situations that are saving lives and making a tangible difference. ESUPS models have already helped reduce response times and improve resource allocation during crises. For example, their work in Madagascar showcases how strategic prepositioning can optimize response efforts in even the most challenging of environments. While ESUPS works globally, we're going to narrow the scope in this case study to one country to create a manageable but realistic problem for you to tackle using Madagascar as an example. This case study is more than a technical exercise. It's a glimpse into how optimization for good can transform global humanitarian efforts. We're excited for you to dive into this case study and see the power of optimization in action. Whether you're inspired to explore humanitarian logistics further or apply these techniques in your other challenges, we hope this example will leave you a lasting impression on how optimization can truly make a difference. So let's get started. Open the notebook and let's explore how optimization is reshaping disaster response with ESUPS in Stockholm. And now I'm going to hand things over to Jerry to walk us through some of the technical elements that you're going to consider before diving into this hands-on notebook. Thanks so much.
Thanks, Lindsay, for all that awesome background information. Before we really dive into the notebook file, I want to take a couple minutes just to talk about what we call in mathematical optimization problem archetypes. And one thing that I've mentioned about mathematical optimization a lot, and we've sort of seen through examples, is that mathematical optimization is very flexible. We talk about all the different industries that Gurobi is in and mathematical optimization is in, all the different problems that we can solve. And the first presentation of Opti 202 was optimization is everywhere. So it is a very flexible tool. That said, we do see sort of very common model structures to solve a lot of these different problems. And when you have these sort of common structures, these are what we call archetypes, and these are studied a little bit more deeply, a little bit more individually, and this can help really get some proven strategies for maybe specialized approaches or understanding key characteristics of these problem archetypes that can be sort of taken advantage of in the modeling process. So you may be familiar with some of these common archetypes, and they're sort of popping up on this screen right now. Knapsack problem, set covering, facility location, network flow, and within that sort of the shortest path, assignment problems, traveling salesman problem, bin packing, cutting stock, transportation. We'll get a little bit more on that one in a minute. These are all sort of archetypes, or at least just common problem names that people like to bin their problems into, just so it's a little bit easier to discuss and talk about what it is. Because if I say, oh, my problem is a knapsack problem, people who are who sort of understand mathematical optimization be like, oh, I know what you're talking about. So each of these sort of have their own little category and their own little characteristics, and it's worth sort of understanding each of them at least a little bit. So what I want to dive into a little bit more specifically is the characteristics of this problem that we're going to talk about today. Well, it is a variant of the transportation problem, and the transportation problem is all about moving goods from multiple sources to multiple destinations, typically at a minimum cost, and there may be other restrictions and characteristics and constraints around that. It's commonly used in logistics, and considering, when you have shipping costs and capacity limitations. So it's a very, very common type of problem. But in addition to being a transportation type problem that we're going to talk about, there are elements of uncertainty. So there are different scenarios that this comes together to look into. And also the objective is an expected value or a long run average. So that's kind of why we dove into the uncertainty thing a little bit earlier today, to sort of give us a little bit of understanding of what that looks like. So this is the transportation problem, and we see it in its algebraic formulation. So if this does look a little bit familiar, that's because we have seen it a lot. We've seen it over and over again, particularly at the very beginning of Opti 101, because this was more or less the original problem that we looked at when we were producing and transporting widgets from supply locations to demand locations. So this common archetype of problem consists of those supply and demand locations. Let's say we have M supply locations and N demand locations. And then on top of that, we have our goal is to transport the items or whatever we're making, or whatever it may be, to transport that at minimal cost. And our decision is to transport or to decide the amount that we transport from each individual supply location to each individual demand location. And of course, we have our constraints, and we're constrained by the capacity of each supply location, as well as we need to make sure that we meet our customers' demand, or whatever demand we're trying to satisfy. So if you sort of think about the parallels of what we had here, all of these things are in our original widget problem, and they're going to be in the upcoming example as well. So a couple interesting things I want to mention before we dive into the problem is, one thing about, in addition to what I mentioned on the previous slide about uncertainty, we're going to see how we can take this archetype problem and modify a little bit, such that we will see how like the supply right-hand side values of those constraints will actually be decision variables themselves. And one other last bit, and this is sort of to go back to what I was talking about, how once you start studying some of these archetypes, you sort of understand some key characteristics of the problem, and you can take advantage of those characteristics. Given the structure of the transportation problem, there are potential guarantees for integer decision variable outcomes, even if you don't declare it. So this is something that you can take advantage of, is if you're modeling this problem and you think, well, I really need to make sure that I can't be producing half of a widget, then there are things that you can do to make sure that is satisfied without actually having to declare your decision variable as integer. Because if you do that, then you're telling the solver and you're telling the model that we have integer requirements, and it's going to then potentially take a little bit longer to solve, because as we learned early on, that MIPS are much harder to solve than LPs, because linear programs are essentially a subroutine. So I think that's about all it for now. What I want to talk about the transportation problem to sort of set us up for the upcoming example. So I'll see you in a second.